Modern physics can describe the universe with extraordinary precision. We can predict the motion of planets centuries in advance. We can calculate the behavior of particles to decimal places that experiments consistently confirm. We can trace the universe's history back to fractions of a second after it began, and those equations still hold. But that accuracy stops at a clear boundary. When gravity is measured on the largest scales, the universe behaves as if most of its mass is missing. Not misplaced, not hidden by distance, simply invisible to every instrument we have ever built. This unseen component outweighs everything we can see by more than 5 to 1. Galaxies, stars, gas, planets, together they make up a minority of the universe's matter. This discrepancy has been measured repeatedly across independent observations for nearly a century. It has survived new telescopes, new detectors, and generations of increasingly precise experiments. Entire fields of research have been built around identifying it. None have succeeded. The result is not confusion and not controversy. It is something more uncomfortable. Despite everything we can measure, model, and predict, we still do not know what most of the universe is made of. For nearly a century, astronomers have been mapping how galaxies move, and very early on, something didn't add up. When scientists began measuring the rotation of spiral galaxies in detail, they expected a familiar pattern. Objects farther from the center should move more slowly, the same way planets farther from the Sun orbit at lower speeds. That expectation comes directly from Newtonian gravity, using only the mass we can see. But galaxies don't behave that way. Stars far from a galaxy center orbit just as fast as those much closer in. In many cases, they move faster than gravity from visible matter alone should allow. This wasn't a one-off anomaly. The same flat rotation curves appeared again and again across different galaxies, measured with different instruments by different teams. The implication was unavoidable. Either our understanding of gravity was incomplete, or there was far more mass present than telescopes could detect. A similar conclusion emerged from a completely independent line of evidence: gravitational lensing. According to Einstein's general relativity, massive objects bend space-time, causing light to curve as it passes by. Astronomers observe this effect when light from distant galaxies is distorted by massive foreground clusters. When researchers calculated how much visible matter those clusters contained, the numbers fell short. The observed lensing required significantly more mass than stars, gas, and dust could account for.
Again, the discrepancy was consistent, and again it appeared everywhere researchers looked. On the largest scales, the pattern continues. Computer simulations of the universe's evolution show that visible matter alone cannot produce the cosmic web of galaxies we observe today. Without additional mass, matter fails to clump quickly enough after the Big Bang. Large-scale structure forms too slowly and in the wrong configurations. Introduce an unseen gravitational component, and the models suddenly match reality with striking precision. Individually, any one of these observations might invite skepticism. Together, they form a coherent picture. Galaxy rotation curves, gravitational lensing, large-scale structure, all point to the same conclusion. The universe contains far more mass than we can see. Whatever it is, it does not emit light, absorb it, or reflect it, but its gravitational influence is unmistakable. Something invisible is shaping the universe.
Once astronomers accepted that something unseen was influencing gravity, the next question seemed straightforward. What is it made of? The most natural assumption was that the missing mass was ordinary matter, just hidden from view. Cold gas between stars, dim low-mass objects, faint stellar remnants that telescopes couldn't easily detect. This idea, often called baryonic dark matter, dominated early thinking. But over time, it failed every major test. Surveys across radio, infrared, and X-ray wavelengths steadily closed the gaps. Hydrogen clouds were mapped. Interstellar dust was accounted for. Stellar populations were counted down to extremely low brightness levels. The numbers never came close. Even when astronomers added up every plausible form of ordinary matter, they consistently fell short by a factor of 5 or more. The universe simply wasn't hiding enough normal material to explain what gravity was doing. That realization forced a more radical conclusion. Whatever this unseen mass is, it does not behave like matter we know. It does not emit light. It does not absorb it, and it does not scatter or reflect it in any detectable way. It interacts, as far as we can tell, almost exclusively through gravity. This property made it extraordinarily difficult to find directly. Beginning in the late 1980s and accelerating through the 1990s and 2000s, physicists built increasingly sensitive detectors designed to catch rare interactions between hypothetical dark matter particles and ordinary atoms. Experiments were placed deep underground to shield them from cosmic rays. Detectors were cooled to near absolute zero to reduce noise. Materials were purified to unprecedented levels. Names changed. Technologies improved, but the result stayed the same. Decades of direct detection experiments, from early cryogenic detectors to massive liquid noble gas experiments, produced null results. No unambiguous signal, no confirmed particle. Each new generation ruled out large regions of parameter space, narrowing the possibilities without revealing what dark matter actually is. At the same time, some researchers questioned the premise entirely. If we couldn't find the missing matter, perhaps gravity itself was the problem. Modified gravity theories proposed that the laws governing motion break down at extremely low accelerations, such as those found at the outskirts of galaxies. In certain cases, these ideas could reproduce galaxy rotation curves without invoking unseen mass. But success at one scale created failures at others. Modified gravity struggles to explain gravitational lensing in galaxy clusters. It has difficulty accounting for the growth of large-scale structure across cosmic time, and it fails to reproduce the detailed patterns observed in the cosmic microwave background, the fossil radiation from the early universe measured with extraordinary precision. Each approach solves part of the puzzle, but never all of it. Ordinary matter doesn't add up. Direct detection hasn't worked. Changing gravity fixes some problems while creating others. No explanation fully survives contact with all the evidence, and that is what makes the problem so persistent. Every solution creates new problems. Despite decades of failed detection, dark matter remains embedded at the core of modern cosmology for a simple reason. Mathematically, it works. When cosmologists model the universe using general relativity and well-tested physics, dark matter isn't added as a convenience, it emerges as a requirement. Without it, equations that describe how the universe evolves stop matching what we observe. Remove dark matter from cosmological models and structures unravel. Galaxies form too slowly. Clusters fail to assemble. The delicate patterns imprinted in the cosmic microwave background, measured with extraordinary precision by missions like WEMAP and Planck, no longer align with reality. The peaks and troughs in those measurements shift out of place. The universe, as simulated, stops resembling the one we see. Put dark matter back in, and the alignment returns. Large-scale simulations, such as the Millennium Simulation and its successors, reproduce the filamentary structure of the cosmos with remarkable accuracy. Galaxy distributions fall into place. Statistical properties match surveys spanning billions of light-years. Across scales and datasets, the same invisible component keeps solving the same problems. This consistency is difficult to dismiss. At some point, dark matter stops being just a problem in physics and becomes something more revealing. It represents a limit. For centuries, progress in science has followed a familiar pattern: observe a discrepancy, propose an explanation, test it, refine the theory. Dark matter breaks that rhythm. The observations are precise, the discrepancy is undeniable, and yet the explanation refuses to arrive. That resistance is not a failure of method, it is a reminder of scale. Dark matter exposes how much of the universe operates beyond the concepts we are comfortable with. Our theories describe forces, particles, and fields remarkably well within known regimes, but the moment we step outside them, the language starts to strain. The equations still work, the interpretations do not. In that sense, dark matter is an act of scientific humility. It forces researchers to acknowledge that accurate prediction does not always come with understanding. We can model the universe's behavior in extraordinary detail while remaining unsure about what is actually doing the work. And that uncertainty is being taken seriously.
Some physicists now question whether the category we call matter is even sufficient. Others explore whether gravity itself may emerge from deeper principles not yet formulated. Still others suspect that the solution will demand frameworks that do not resemble particles at all. These ideas are not embraced because they are elegant, but because the existing toolkit may simply be incomplete. Importantly, none of this implies that science has stalled. Not knowing is not a retreat, it is an honest boundary. Throughout history, moments like this, when observation outpaces explanation, have preceded major shifts in understanding. They signal not confusion, but readiness for change. Dark matter sits at that boundary today. Whatever the answer turns out to be, it is likely to reshape more than a single field. It may alter how we define matter, how we think about forces, or how we describe reality at its most fundamental level. And that is why this mystery matters beyond physics. Uncertainty in science is not the end of progress. It is often where progress begins.